In this video we discuss concentration cells. Alright, so here you have the Nernst equation that allows us to predict what the potential of a cell would be operating under any conditions of concentration that we wish and 298 Kelvin. Now there's something very interesting about this equation, and that is that even if you have a battery in which the standard potential cell is 0, you can still get a battery, a spontaneous electrochemical reaction, if this term is not 0. Okay, as a matter of fact, if you want a spontaneous battery, right, if you want to extract electrical work, what you would like to have is a term here that is positive, and what that means is that your Q needs to be a number less than 1, so that when you take the base 10 logarithm, that is a negative number, and then with that negative sign gives you a positive voltage for your cell, right? So again, even if you have here a 0 cell potential, if you have difference in concentrations, you can still build a battery, right? So the question is, well, why is this important? What reactions have a standard cell potential that is 0? Well, as a matter of fact, you can actually build a battery with a standard cell potential equal to 0 if the electrodes are exactly the same. Okay, so think about the following battery. Suppose that you're actually running the same reaction but backwards in each one of the electrodes, right? So here you're going to write, for example, copper, and then copper 2 plus to generate copper solid, and then copper 2 plus. Right? It looks like in this reaction you're not doing anything. You have exactly the same reaction products, and that is true nominally, but if the concentrations to start with are different, then you actually are going to be able to get some electrical work out of this. All right, so let's try to go slowly and explain how this concentration cell works. Right, notice that here you have a reduction. All right, so that will happen in the cathode. That is your reduction, and you're going to be putting this in the cathode. And here you have an oxidation, which is in the anode. All right, so we can come here and say, well, in the anode, what I actually have is this oxidation. So you'll have that the standard reduction potential for that will be copper 2 plus to copper, and then the standard reduction potential will be here copper 2 plus to copper. All right, again, you're running exactly the same reaction, but the difference is now that the concentrations are actually going to be different in each cell, right? So here in the cathode, we're actually going to have a concentration of 1.0 molar of copper 2 plus, and in the anode, we're going to have a concentration of 0.10 molar copper 2 plus. And that difference in concentration is going to be enough to actually drive the reaction. Right, so how is this going to work? Well, we first calculate what the standard potential will be for the cell to calculate that ingredient of the Nernst equation. And notice that in this case, right, you will have that potential minus that potential. That is going to be the same, right, under standard conditions. That is going to be 0. What is going to be different, though, is this term, which we hope is going to make our potential of the cell positive, so that we can extract electrical work. Right, so E cell then is going to be equal to 0 minus 0.0591, the number of electrons transferred. Notice that in this case you have 2 electrons transferring, right, from 2 plus to 0 and from 0 to 2 plus. And then here you have your logarithm of the reaction quotient, which will be the concentration of copper 2 plus here, and notice that that is working on the anode. Okay, so that's what we have, divided over the reference concentration, 1 molar, and here you will have your concentration of copper 2 plus in reagents. But notice that in reagents, right, that copper 2 plus is in the cathode, so that will be the concentration of the cathode, divided over 1 molar. Okay, so we come to our design here, and in the cathode, we have a concentration of 1 molar, so if we can replace this by 1 molar. In the anode, we have a concentration of 1/10 of a molar, 0.1 molar. So then what that means is that we can come here and simply replace that by 0.1 molar, right? So all of the units cancel. And notice that what is left over is simply this term, and the based on logarithm of 0.1, which is going to be -1, right? A negative number. And what that means is that you're going to make a battery, which is possible. And the voltage here will be 0.03 volts. Right? So that's not a lot of voltage, but still, you can make an electrochemical reaction go forward, all right, if you have the same electrodes but different concentrations of some of the redox pairs. Okay? So this is what is called a concentration cell, and it's a nice application of the Nernst equation.